going through the warm-up real quick. I did a little walk around. All of you got number 1 perfect. We don't even really have to talk about it. So, lovely partial x, partial y, negative 12z over x plus y to the 4th. Every single group got it right. Were there any questions on number 1? Number 2, find the directional derivative of x e to the y in the direction of cosine theta, sine theta at 2 pi thirds. So I didn't give you a point there, so it just had to be a generic answer with x and y. I saw one mistake on one whiteboard, but it wasn't from calculus. Well, okay, I saw one mistake and one like lazy evaluating. So, but it wasn't from calculus, it was just not knowing the cosine of 2 pi thirds and the sine of 2 pi thirds, right? So what is the cosine of 2 pi thirds? Negative 1/2, and the sine of 2 pi thirds is positive or 3 over 2. So we had these kind of stuff in this one, right? That's okay. And then, of course, on that backboard, would I accept, see the one that's circled under Mirzakhani? Would I accept that e to the y times the cosine of 2 pi? No.
Unacceptable.
Unacceptable, right? Okay. Yeah, we don't leave our answers in unsimplified trig form. Okay. Good. All right. But apart from that, those looked really good. So, any questions on number 2? Because I'm happy to work Andy's out. All right, number 3. Now we're doing a directional derivative. We have a point, and from that point, we're pointing the direction of 0, 0, 0. So I was hoping you would find a vector from 2, 4, 0 to 0, 0, 0 here. Haha, like here. So you end up with the vector negative 2, negative 4, 0. But then, of course, you have to turn it into what kind of a vector? Unit vector, right? And then your directional derivative is your dot product of your, is that the gradient? I don't know. Let's see. Where's your gradient?
Oh, yeah, it is.
Is that it?
Yeah,
okay.
It is.
Okay. So it's the dot product of the gradient and the unit vector. So I got, well, I reduced. So negative 2, negative 4, 0 over root 20, or negative 1, negative 2, 0 over root 5. Which is that this? This is your final, I can't tell. Wait. Oh, wait. That's just me writing you. It's got to be an answer. No, because it's a dot value. It's got to be a number. 8 over root 5. There's my final. Yeah, which is equivalent, right? Because you pull out a 2. Except you guys got to, it is negative. Okay, good. So negative 8 over root 5, negative 8 over root 5. You drop the root 20. Casually. You casually drop the root 20. Okay, so that's the only thing we need to learn is that it's got to be a unit vector, right? Okay, so a little learning. Good. Yours is on the far one. Where's your answer? The one that's circled?
Well, I didn't. Is it the reason I was and I didn't have this
the 4 over 5 comes. So that's your like directional vector. But it doesn't actually get the slope. Okay. So we really are looking, we're talking about directional derivative, we're really looking at that slope. Right? Okay. All right. You reduced on? Okay. Okay. Pulled out a 4 instead of 2. Okay. Good. 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 All right. All right. So a few small mistakes. That's okay. Are there any questions at number 3? Do we need to walk through it more slowly? Maximum value of the directional derivative. What gives us the maximum value of the directional derivative? Oh, it's that gradient, right? Okay. So of x, y squared, z squared at 2, 1, 1. Let me make sure before I start talking like it's the answer. All right. So find the gradient at 2, 1, 1. And then the actual maximum value, like the magnitude of the gradient.
I told you it was 1, 4.
What's the matter?
Got it wrong. For the partial x.
Oh, your gradient was wrong?
Yeah. It looked like the y.
So you had the right gradient, y squared,
The
z
y
squared.
with the x.
Oh, you just had, oh. You know what's odd is you drew these y's with little curly q's, but then this y looks like, it does look like an x.
That's human error, right?
That's human error.
Human error.
Okay. Okay. Good. Beautiful. That's gorgeous. Very nice. Very nice. 2 in a row. Wonderful. Beautiful. Well done, ladies. All right. Let's see. Here it is. Found it. Good job. Okay. Yep.
Curly.
Nice. Half.
Okay, so you found the gradient, and then you just wrote the gradient as a unit. Okay, so it's just the magnitude of the gradient is the size of that direction. It's just there. So there's your gradient. Write your gradient as a vector, not as a last one, we're almost done. Equation of the plane. Ooh, tangent to x squared plus 3z squared equals y. So in this one, you're going to have to get everything on one side to find your gradient vector and then use your gradient and your point. So let's see. So I had a vector of -2, -1, 18, and then this is my unsimplified plane equation, and that's my simplified. So we have y minus 28 equals -2 times x plus 1. This is perfect. Well done. This is written different, but it's perfect. Good. 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 Gorgeous. Good. 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 Yes. Wait, let's see. It's the z. Something happened with the z. Oh, is that this? Does that say 18? And I just can't read it? Okay, good. Then you got it. Well done. All right, good, good, good. Yes, Dorsa.
Wasn't there a problem like on the last test about like the equation with like the plane with the tangent line?
There have been lots of questions about equations of planes.
Do we use this technique then, or is it a different thing?
So back then, in chapter 12, when we asked you equations of planes, we would just give you two vectors on the plane, and then you had to create an orthogonal vector. How would you do that? Cross product, right? It was really just to get you to learn how to do a cross product and know that it produced an orthogonal vector, and then know how to write an equation of a plane. So that's what we did in that first unit. We did a lot of equations of planes that way. Now we're using gradients. But yeah. Yes?
Wait, so for this problem involving the equation of the plane, we're just accepting that the gradient is an orthogonal vector.
An orthogonal vector, which we haven't talked about a lot. We just talked about a little bit.
Okay, so that's like the stuff that we did last class, right? Somewhat.
2 classes ago. Yes. Yes. All right, let's get started. Today we're doing 14.7a, which is our first day on extrema. Today is relative extrema. Tomorrow is absolute extrema. Tomorrow is a slightly more complicated process than today, and we have a shorter period tomorrow. So we're gonna kind of move tomorrow. We won't be no lollygagging tomorrow. But anyway, but today is still, I have a good solid lesson in here today, but the concept, the procedure is that. All right, everyone ready? Finding relative extrema in 2 variables? Okay, Maud's ready. She's nodding her head. Here we go. All right, so before we start, let's talk about, you don't have to write this. It's okay. Let's just talk about it. All right? So, okay, so we have an extreme value theorem. You had an extreme value theorem last year. Anyone remember the extreme, if I covered this up, anyone remember the extreme value theorem from last year?
If it's like a definite, continuous on a definite interval from like A to B, then that there's gonna be a max
function that's continuous on a closed interval has a max and min, right, on the interval. So now, since we're in 3 dimensions, instead of being continuous just on an interval of x's, now we're going to be continuous on over a plane, right, over a region. And so if we have a closed region, then there's going to be a max and a min. So let f of xy be a continuous function on a closed bounded region R. So that whole thing, what does it mean to be over a closed bounded region? So bounded essentially means there are boundaries. Enclosed means you include the boundaries, right, in your region. It's kind of like closed interval, right, versus open interval. So we include the boundaries. So every continuous, if we've got any kind of, it's easiest to picture like graphically. So every function that's continuous over some closed region has to have a max and a min over that region. For when we're talking, these would be more like absolute. Would our answers, if I asked you like, what's the maximum value of this function, what kind of a value would it be? A z value, right? It's the highest z value or the lowest z value. So anyway, so closed, this is just kind of an intro to the unit, to the section. So there has to be at least one point in this region where our function has a high point and where our function has a low point. There can be more than one place where that occurs, but there's only one highest z value and one lowest z value over the region. But they can occur ever. I mean, if it's a plane, that's flat and parallel, every single point can be a max and min, right? But still only one highest z value and one lowest z value. All right. So lucky for you, we don't have to take an AP exam, so you don't have to sit there and learn the hypotheses and the conclusions. But today we're going to talk relative extrema. So we have 3 things that can happen when we're talking about relative extrema. We can have a relative min, we can have a relative max, or we can have what's called a saddle point. So when you have a relative or local min, it's very similar to last year when we did it in 2 dimensions. So if we have a function like this, so this point right here would be a relative max, relative min. This is a relative max, and it's also a what? It's where the absolute max is. Does this function have an absolute min the way I've drawn it? No. So a relative max or a local max is the maximum in some interval, right? In some little open interval that surrounds the point. Same thing with a relative min. It's the minimum value for some little local interval that surrounds the point. Well, when our input isn't just x's, when our input is ordered pairs, then we're talking about our local min being the minimum value over some small region. So they call it this little open disk. Really, it's just like if you kind of picture a little circle around the point. If that point is the minimum value for some little circle surrounding the point, then that point's called a local min. Same thing if the point is the maximum value for some little circle of points surrounding the point, then that point is a local max. And it's just like before. So local max would be like top of the hill. Local min is like bottom of the valley. Saddle points are new. Well, we've talked about these already, right? A saddle point is both a max and a min all in one point. So you have to kind of be able to visualize it. So if I'm looking this way, then this point is the min. But if I'm looking this way, it's hard to see it. Kind of think like that, right? If I'm looking that way, it's the max. But if I'm looking this way, it's the min, right? So when you have both, depending on the direction, you end up with what's called a saddle point. Yeah. It's only what? An absolute saddle point? Yeah. You don't really put the word local at all with saddle point. It's just a saddle point. Okay. All right. So how do we find these? Before I show you this, do you guys remember last year we learned 2 ways to find relative extrema? The first way was called the first derivative test, and we would find our critical numbers, and what would we make? Make a sign line, right? Yeah, and then we know that our maxes are where the first derivative changes from positive to negative, and our mins are where the first derivative changes from negative to positive, right? We learned a second test called the second derivative. Oh, Aubrey's nodding. The second derivative test. Does anyone remember the details of the second derivative test? Yeah, Ian.
So once you derive it the first time, you have to derive it the second time. So if your first derivative produces a 0, then you proceed to test the point of the second derivative. If it's negative, then you have a local maximum. If it's positive,
Beautiful. Very nice. All right. So the test we're going to be doing today is just like the second derivative test. Well done, right? Okay. Good job. All right, so here's your steps. So the first step that you have to do is find your critical points. Finding critical points when we're in 3 dimensions is a little bit trickier. Before you could just find your derivative set equal to 0, kabam. Now you've got 2 partials, right? So you have to find your f sub x and your f sub y. Remember for you to have a critical point, they have to both be 0 at the same time. So you're setting partial x equal to 0 and partial y equal to 0, and often it's going to generate a system that you're going to have to solve. So you set partial x equals 0, partial y. You could also have a critical point if one of your first partials are undefined, but I don't ask you. Anyway, they're all going to be 0 in this one.
But so it could still be a critical point even if it's undefined, right?
Absolutely.
If it's like 1 is 0 and 1 is undefined, even if we're not asked that.
If one of the partials is undefined, it's a critical point. Something weird is happening there. So what happens if your first partials are both 0, you end up with a horizontal tangent plane, because you've got slopes. Basically, all your directional derivatives are based on your first partial, so you end up with directional derivatives that are all 0. So you end up with a horizontal tangent plane, which means you're kind of at the top or at the bottom of something, unless you're at a saddle point. So. Anyway, all right. Every max and min that we do for today, all of our local maxes and mins are going to occur at a critical point. Second partials test. So you found your critical points. So you set your first partials equal to 0. You've solved your system. You found your critical points. This is what we're going to use to test them. It's called the second partials test. Our new book calls it the second derivative test. So I like to call it the second partials test just because it helps my brain keep it separate from our Calc 1 stuff. So, all right, so if we have a critical point, then we just have this little identifier called D. I don't know what D stands for. If D is like the discriminant, determinant, I don't know. Do you know what the D stands for?
It's a combination of both of you say.
Oh, okay, there we go. There you go. So anyway, so our D, so it's going to be our f sub xx, so our second partial with both x's, our second partial with both y's, and then minus the mixed partial squared. So you do f sub xx times f sub yy minus the mixed partial squared, and that gives you your D. If your D is positive and your f sub xx is positive, you have a min. If your D is positive and your f sub xx is negative, you have a max. So my brain, I just remember if my D is positive, then I'm going to have a max or a min. If my D is negative, I've got a saddle point. If my D is 0, then I'm kind of stuck because the test doesn't really work. Then you got to kind of look at the graph and see what's going on.
Is there no alternative to do, like, to approach the problem with the D is 0? It's just...
I'm sure there is, but not anything that we're going to do in here. I do give you one where the D is 0 just so you can see what's going on. Oh, a little trick. If you can't remember D is actually it's the determinant of the matrix of second partials. So if you set up a little matrix f sub x, f sub your mixed partials along this way, and your like f sub x, and f sub y on this diagonal, and do the determinant, you get D. If that helps you remember it. That doesn't tell you what to do with the D, but at least it helps you find the D. You say it's inconclusive and move on. We'll look at the graph. We'll pull up the graph and graph it today one that's inconclusive. Yeah. So if you can't remember how to find D, so put your xx, xy, yx, yy, and really these should be the same. So the determinant, remember, you do multiply down and then subtract multiplying up, right? So this times this minus this times this, which is the same thing as what we got up there. So it's just a little memory trick.
I'm assuming we're still going to write our justifications, right?
Nope.
Oh, no.
Your work is going to be your justification. You don't have to write a because statement. I put a little note in here that when I'm talking here about the f sub xx, that you could do the same thing with yy. You don't have to use xx, either one, because if your D is positive, that means these two things both have to have the same sign. And if your D is negative, then you're going to have something different going on. But if for all of your maxes and your mins, if your D is positive, then this product has to be positive. It's the only way to get a positive D. So you either have to have both positive or both negative. So it actually doesn't matter which one you use. All right, are we ready? Okay. Oh wait.
I didn't see the note again.
You don't have to write the note.
It'd be kind of useful though in like a situation.
All right, everyone good? Oh, suggest you need another minute?
No.
You sure?
Yeah.
Okay. All right, so we're going to find the relative extrema of this beautiful cubic. What's the first thing you're going to do with this? What did you say?
Find the partial x.
Find the partials, first partials, yeah. All right, everyone have their first partials? Okay, set them both equal to 0. I think I've got my partials right here. Check your answers, see if they match. Are we good? Yep. Okay, so set these equal to 0. You're going to end up with a system. See if you can solve the system. Feel free to talk to each other.
Four x equals 4y. So this is the so x equals 0. Or 16. Maybe for x
Once you find your x values, there should be 2 of them. Then you've got to write them as ordered pairs.
oh yeah. So 0, so 0, 0, and then 4 thirds, and
Yeah.
so then 4 thirds and negative 4 thirds.
Good.
Oh wait, that's no, it's 4 thirds. It's 4 thirds
Never
positive.
get the point 0, 0, and everyone that I've seen
4x minus
0, 0,
4
4 thirds, 4 thirds. Is there
So
anyone who's
Yeah.
stuck or confused?
so just 4 thirds, 1 thirds.
All right. Once you find your critical points, what do you need to do with them now?
Find the
You got to find D, which means you're going to have to find your what? Second partials. They're not bad. These are easy.
So 0, 0, and 4 thirds, 4 thirds.
Do you know why it's 0, 0? Because the x's you found were just x values, and then you need a place to plug them back in, and the easiest one was when you found the equation x equals y, because they have to satisfy all those.
So I got x partial x is
Well, you are doing
x, x y is 4, y x is 4, and y is
Oh, okay. Alright, so that. Alright, we got that. So now if we find D. So you're going to find a D value for 0, 0 and a D value for 4 thirds, 4 thirds. You're going to have 2 different Ds, one for each point.
Yeah, so x y is 4, y x is 4, y is negative. Yeah, then x y and y x are equal to 4. So now you find like the difference.
Okay. So now you got to figure out based on that. Once you find your D's, see if you can figure out what each point represents.
So you have 24x,
4 thirds, 4 thirds.
so 24 times 16. So do we plug in the x?
What did you get for D?
Yes.
Okay, so 0, 0,
And have so D is
yeah, so if it's less, so that's a solid point.
so D
And
at
the
x
other one
equals
was
0.
You just plugged out of that.
Equals negative 6. Then
And you'll always have some.
saddle point, right?
The first one is
Saddle point.
0 to 0.
Yeah, saddle point.
Yeah, negative 24 over 3.
So 8 times 4, 32, 16.
Yeah, negative 16.
Yeah. So then that's greater than 0. So and then you plug in that. So then you got negative.
No absolutes today,
If
just
you
locals.
relative max.
No absolutes, just locals.
Greater than 0.
Why would you value the whole positive? So you're gonna have two different.
Yeah. Okay. So then
What does it matter though?
So then it'd be about.
As long as like, no matter what, if p is less than 0 is going to be
I don't know if you remember it's the same with yeah.
So it says like for saddle point, if p is less than 0, then
Okay, so at 0, 0, I got a negative d. So what does that mean we have?
saddle point.
Saddle point, saddle point. When you write your actual point though, I want the x, the y, and the z. I want an ordered triple. Okay? What? What? So my point was 0, 0, 1. How did I get the 1? How did I get the 1?
Original function, right?
Original function. Right?
Okay, I believe you.
Okay. So this point, this is just a point on in our xy plane on the region, but the actual answer for the saddle point or the min or the max, those should be points on your surface. So those should be ordered triples.
Calculator. Calculator time.
For the 4/3, 4/3, what'd you get for D? Positive, negative?
Positive.
Positive D. So then you have to check your f sub xx, and what was f sub xx? Negative, is it negative?
Yeah.
Okay, so that means you have a local max, right? So we've got a local max at 4/3, 4/3. I don't want to give away the point. Okay, so since we have a local max, I want the x, the y, and the z, which you're all pulling out calculators now. That's okay. You're going to wait and just get the answer from everyone else?
Find out the z value to get
What's the matter?
Is that 0 or that 2? Give me my hand. I got 2.
No, I got 59 over 27.
Why am I right? Suck. Like, I can't remember. Yeah. Let's go. I got 2.185, 185, 185.
I got
That's why I got 2.
Oh, wait.
why does that
Oh, are you using the right one? Because you have negative 6x.
That's stupid.
There we go. All right. Do you guys want to graph this in Grapher for a second?
Yeah.
Yes. Take a second. Put this in Grapher. See what it looks like. I will do it as well.
No.
I have the graph written here, but I'm going to do it in Grapher. We'll see what it looks like. And just so you know, I forgot to stop the recording, so if you're watching the recording, it's going to have that whole little spiel. Okay. All right, tell me the equation. Negative x cubed plus 4xy
Minus 2y squared plus 1.
2y squared plus 1.
Here my handwriting.
All right, so here's the point
4/3, 4/3. Here's the point. Like, if you look at 0, 0, 0, does it look like it's a saddle? Right? See how it's this way, it's a min, but if you look kind of this way, it's a max. And then this must be the point 4/3, 4/3, whatever that z value is, which is just a regular local max. No other local extrema. Just those two interesting points. Kind of a fun little graph, right? Okay. Let's try another one. We have one more very similar. 2x squared plus y squared plus 8x minus 6y plus 20. You want this on whiteboard?
Yeah. No, I need
All right. I give you 4 minutes.
I wanna run it out. I gotta do something. Oh. Sit down.
Yeah, you can erase it. Pause this.
All right, so first partial, second partial. The only critical point was -2, 3. It was the only way for the partials to both be 0 at the same time, right? Was at that point. All right, so then we find our second partials. This one was easy. They were all constants, right? So life is happy. So we end up with a d value of 8, positive 8. So since our d is positive and our second partial with respect to x is positive, we have a relative min. So plug into the original function, and we end up with a point of -2. Wow, it's like magic.
I'm not gonna mental math.
The z values change. -233. Very good. All right. Okay. So what does it look like when the test fails? It just fails. Give this one, take a minute, try this one.
We already know. Let's just say
Disagree. What can you even do? I don't get it. Y equals 0 Well, actually, it could be 0 as long as one of them is 0.
Ah.
For an infinite number of
Ah.
So,
Oh, yeah.
how do I point to 0, 1? Oh.
Okay, so I don't know if you guys heard Jack. So you find your first partials. So anytime x is 0, both of these will be 0. And anytime y is 0, both of these will be 0. So we have infinitely many critical points, right? All right, so the thing is, if we go ahead and find our second partials, so you get 2y squared, 2x squared, and 4xy, when you square them and go ahead and multiply out and subtract, you end up with a d value of 0 for every single critical point, no matter what. So the test is actually inconclusive. If you look at the actual graph, I'm going to graph it in grapher so you can see it better. So this is x squared, y squared. All right. X squared, y squared. So if you look at the actual graph, oh, did I turn it upside down on that thing? Looks upside down.
You have negative x.
Oh, I have a negative. That's why. Thank you. There we go. Okay. All right. So if I graph x squared, y squared, this is along each of these axes. Every single one of those points is a local min, right? So you get infinitely many local mins. Woo! I love spinning this thing. Anyway, so there's your graph. Okay. All right. Contour maps. What?
Oh my god.
This is not a nightmare. All right. I don't want you to do any discriminant or determinant or D stuff. All I want you to do is look at it and think about it and talk to your groups. All right? So I'm only asking you to classify at the points 1, 1, and 0, 0. I can also ask you for -1, -1. But let's just, since those aren't labeled, let's just do 1, 1, and 0, 0. I want you to talk to each other about whether each of those points is a max, a min, or a saddle.
Like a mountain. Yeah, call it saddle.
Because it's decreasing in this way,
So it's like it's kind of
Oh, you're right.
yeah.
And then 1, 1 is a max. Think of it like a mountain. Probably ours.
the equation. I don't know if 1, 1 is.
You're right. Yeah, 'cause it's going down and
Oh, is that super backwards?
Yeah, so, oh yeah, it's probably
First,
okay,
they
so
were
it's a local mint, my bad. It's going down in number. It's like it's sloping down. And then 1, 0, 0, so it's like going up and then.
All right, you guys, are you good? Or do you good? Do you want to explain what you got? Okay, say it up. Quiet down. All right, Brown, say that again a little bit louder.
So we got a local min for 1, 1.
So why a local min here, not a local max?
Because you come from any direction. If you come from any direction, it's getting smaller.
Ah, yeah. So if you look at your, like how the level curves are labeled, they're decreasing as you move in, right? So assuming that the trend continues, then this is going to be the lowest point inside of this level curve right there. So it's min. Good. What about at 0, 0? All right. Someone hasn't spoken. Zach, did you say saddle point? You thought it was a max? Ryan, did you say saddle point? Do you want to explain why?
Well, if you go one direction, it's decreasing.
Ah, so if you look at this point, and if you go this way, right? So this point has a z-value of 1. If we go this way, we're at 0.9, 0.9, right? So we're kind of a max this way. But if we go this way, we're at 1.1, 1.1, so we're at a min, right? So you'll see those kind of like criss-cross directional things. You usually end up with a saddle point. So yeah, 1, 1 is a min, 0, 0 is a saddle point. And I'm going to pull up the book's little explanation of this just so you can see it. Okay. So what they show you here, this is the one very similar to what we just did. So if you look at your figure, it's hard to tell. You have 2 mins and then you have a saddle point. The saddle point's not as easy to see with this coloring. You can kind of see though. It's a max this way and then it's a min that way. Looks like a tooth. Anyway. All right. So this goes with this graph. If I pick a different surface, all right, take a look at that, look at the graph, and then look at the corresponding level curve. And then in your groups, I give you 20 seconds, like not 5 minutes, like 20 seconds, talk about what's going on at this point right here, and then what's going on at this point right here. All right, 20 seconds. None of the level curves are labeled, but you can use the graph to help you figure out.
Yeah, it's like that.
All right.
Yeah, I won.
Amal. Hi. How are you doing? Good. What's going on at this point right here? Oh, okay.
We need more time.
You need more time?
Of course.
Well, we know
It's not enough time.
Okay, take a look at this, the corresponding graph. This is that point. Yeah, it's a min. Whenever you have like a point in the middle of all those level curves like that, it's either going to be a min or a max. And then you just look at your, since they didn't give you label any of them, you can use your graph to decide it's a min, right? What about with this one where you get this kind of crisscross thing here? That's a saddle point, and that's this point right here. All right. Are there any questions that would agree on that one? All right, one more, and then we're going to do some application. Okay, so this one, let's see, what have we got going on here? We have a point here, and an interesting point looks like right over here. Maybe we've got like a saddle thing going on somewhere in between. It's hard to tell. Maybe if I turn it like that. There we go.
Yeah.
The one like at 0 is very cool.
Yeah. So whichever one goes with this one, which I'm thinking that's this point, that's the one at the origin. So what have we got here? We got that's a min. What about this guy right here? That's your max, right? And it's kind of occurring here. Here. Kind of weird. All right. So let's get back. Okay. So in the past, I used to do applications on a different day, and then I realized, oh, this book doesn't do that. They have like applications blended in. So we're going to do a couple application problems, and then once we're done, we're going to talk about quizzes, and we'll call it a day. So first application, we have an electronics manufacturer. I know the electronics in this problem are a little bit outdated, but yes, DVD recorders, they used to be a thing. Nobody does them anymore. Let me move this over so you can see the function there. Okay. All right. So an electronics manufacturer determines that the profit P in dollars obtained by producing X units of a DVD player and Y units of a DVD recorder. I'm going to move this over so you can see better. There we go. All right. So X units of a DVD player, Y units of a DVD recorder is approximated by this P of XY model. 8x plus 10y minus 0.001 times the quantity x squared plus xy plus y squared minus 10,000. Find the production level that maximizes profit, and what is the maximum profit? But by production level, we mean how many DVD players and how many DVD recorders should they produce in order to make a maximum profit, and what is the maximum profit? All right. It's exactly the same as what you've been doing. The only difference is now you have words. Right?
I agree with that statement.
Oh, yeah. I thought I was thinking we only have partial y. It's like, what's going to happen because of last year? We'll be like, we find like y times, we find like the.
That's because there was only one input there.
Yeah, now it's two.
Yeah.
else got it.
So what are you gonna do?
It's a rate of change when you have a rate of changes in that, not when you're an amount. Right, so, yeah. Brian, are you done?
I got
Can I see what you've got? But what's a relative? How did you get that without a point? Your second partials were all constants? Oh, well, that's kind of nice. So whatever point you find, once you find the point, you know, all right, so you gotta find the point. It's a nice little system. Why are you erasing? Wow. Do you always do combination when you can? Instead of like elimination, instead of doing substitution? Okay, that's fine. They're both perfectly valid. They're a pain. Yeah. Yep. All right.
Oh. You didn't? I got negative 4,000.
Not the proper negative. I definitely.
Yeah, but also,
I didn't use something.
also X and Y can't be negative. Neither of them is bad at math. It's bad at math. What did you get for X and Y?
Oh, I never had a minus.
Wait,
So why would it be positive if a negative problem?
Wait, what do you get for your I plugged in the equation.
Why am I gonna get this?
Yeah, I get 4,015.07537.
That sounds horrible.
You guys actually have problems with points.
Okay, let's say like it's
No, we're
500.
God, I hate
Kind of like
I got 2,000.
yeah, 2000.
Wait, X 1,000? Oh, let's go. And then you plug in like the X into. Hey, wait, these like, wait, where do you plug in the X into? So we'll plug in the X into.
Oh no, I didn't know.
Oh, yeah.
So it's positive, is positive.
Yeah, okay, that's fine. I got
Oh, this will take forever. Oh.
It's not that bad.
Oh, wait a minute. I just gotta believe. I just gotta believe. I put up 0, 0, 4,000. Y was 4,000. 2,000, 4,000. And then you gotta find the other partial.
So it's 1,200 to find the negative.
Wait, so then for x I got negative 10,000.
So Anna said she got 400.
So right, it's
So partial x is negative 0.02. Partial y,
It's 4,000.
yeah.
So you have to find the other
Yes, you do.
Well, I had that y equal.
Plug it into one of the systems.
Yeah.
What does x represent?
So I have partial y is equal to negative 0.0.
How you find
You-
And then partial x is equal to
I got negative 10,003.
Oh, I have multiple.
No, you don't.
is negative 0.0. Partial y x
What is that?
4 times 10 and partial x.
So we find that's our p, that's our partial x, there's our partial y. So I went ahead and solved the system. I ended up with an x of 2,000, which everyone eventually got there, right? All right, and then I got a y of 4,000. Now, what I didn't do last year, oh wait, did I? No, I didn't. Is I didn't verify my d's, and I really should have, so I was going to write this in today. So p sub x, x. So my second partial, so I get a negative 0.002. And then my piece of y. So I get also a negative 0.002. Tell me if I mess up. Piece of xy. So negative 0.001. All right, let's see. So my d, these are all constants. So my d is going to be 0.002 squared. So what's that? 0.00004. Okay, plus or minus 0.00001, which is positive, right? So I have a positive d, a negative second partial, so I have a relative max, right? So your d is just really to verify, to make sure that you just didn't find like the worst possible scenario for production. You found the best possible scenario. So the level that you want is 2,000 DVD players, 4,000 DVD recorders, and then your max profit is the z value, which is $18,000. Does that make sense? All right, I know we're beat. Can we do one more? Because we haven't done one with geometry yet.
Oh my God.
Would you rather work on quizzes?
Yeah. The first quiz, yes.
I know we did. I know. I'm thinking one more. One more. All right. Okay. Oh my goodness, how much fun is this one? Right? Okay. Hey, I gave you, it's a rectangular box. It's not like it's, you know, a cylinder with something on a half hemisphere on top or anything, right? Okay, so a rectangular box is resting on the XY plane with one vertex at the origin. The opposite vertex lies somewhere on that plane. Find the maximum volume of the box. So you're going to have to find the point that causes this to be a maximum. Now, first thing you want to do is write an equation for what you want to maximize. What are we trying to, because we don't even have it. They didn't give us an equation for what we're trying to maximize, right? So what are we trying to maximize here? Volume. What's the equation for the volume of this box? X times Y times Z. How many input variables do we have in this equation?
3.
We have 3. How many have I been teaching you with? 2. So could we get rid of the Z?
No.
Never.
Yeah.
Do we have any other information?
That.
We have that, right? So what we're going to do is solve that for Z. So Z equals 8 minus 2x minus 4/3 y. You're going to solve this, substitute it in for your Z, and now you're back into the same max-min world that you've been in before. So right now, let's just stick with 2. First, are you doing it on the whiteboard?
I was wondering if you we did that too, just to discuss.
I didn't give you guys a brain break today either.
Oh.
Yes. So then, the second partial test is inclusive. Have you found your?
I mean, I was like, I didn't do like the actual. I don't know. I didn't finish it.
Yeah. Are you sure? Yeah. Are you sure you're doing your partial test? That 8 minus 2x minus 4/3 y, that's not my function. Yeah, I gotta substitute that in for z in my x times y times z function. In your in your volume function.
All right, my bad.
Yeah.
That makes more sense.
Oh, thank you. All right, so there's my volume function.
Oh, you substitute.
Oh, whoops, yeah. You get 8x minus 2x squared minus 8/3 xy, right? So look carefully at your v sub x. Do you have something in every term that you can factor out?
Oh, yeah, I do.
What do you have?
I use this and then have a
First one down, y.
You have a y, right? You could pull out even a 4y if you wanted to. So we have 4y. Write down, please. 2 minus x minus 1/3 y, right? We want that to equal 0. For this guy, if we pull out a 2x, we're left with 4 minus x minus 4/3 y equals 0. So for this to equal 0, either y has to equal 0 or this has to equal 0. For this to equal 0, either x has to equal 0 or this has to equal 0. So what you end up with is you end up with this ordered pair of 0, 0 from this part, and then whatever you get from this system. 0, 0, what kind of a volume is that going to give you? It's going to give you a 0. It's not even going to give you a box, right? Okay. Plus, that point won't even be on the other plane. So 0, 0 doesn't help you at all. So you're really looking at the solution to the system in order to find the critical point that you're looking for.
Michelle's good point.
What was your X value? 4/3. Did you get the same thing? Okay. What did you get? Oh, for your final answer for the volume. What was your X? 4/3. You got 4/3. What did you get for your X value? 4/3. Ian in the back. Did you get an X value for your critical point? Not yet. Do you need some help?
Yeah, we plugged in the critical values.
Okay. Vikram, did you get a critical point?
Yeah, 4 with you.
All right.
No, you don't know. No, they're on this week. Yeah. You gotta go to like that bell section. It's like your notification section, and it says, "Did you connect it with Reddit?"
I've connected with Reddit.
Oh yeah, I didn't see it until today.
Because what kind of a volume is 0, 0, 0? Because one vertex is a 0, 0 and the opposite vertex is also a 0, 0. And it wouldn't make any sense anyway because the opposite vertex wouldn't be on the plane that we asked for. So, well, I guess it would if you had 0, 0 and then a z value of 8. Yeah. Okay. So anyway, yeah, so it looks like just about everybody got the point 4/3 too. So our maximum value is 64/9. Again, I was lazy last year when I made these notes and I didn't verify that it was a max. So if I really wanted to be good and get full credit, I would actually find my D and verify it, which I should have done. Did you guys verify? Rishi, did you verify? No? Did you just assume? What if that was the min?
Yeah, what if that was
the major?
That's tough for you.
That's okay. All right.